Hi, my name is Alessandro Umbrico. I'm a researcher at the National Research Council of Italy and I present a joint work with other colleagues of the Institute of Cognitive Sciences and Technologies entitled Modeling Affordances and Functioning for Personalized Robotic Assistance. Socially assistive robotics is a growing research field aiming at realizing robots capable of socially interacting with humans and provide them with continuous and personalized assistance in common life situations. Such robots should be capable of personalizing and adapting their assistive behaviors to the specific health needs of users, as well as the desired assistive objectives. It is necessary to endow these robots with heterogeneous capabilities like example perception, common sense, reasoning, or planning to successfully carry out the desired assistance under different conditions. Artificial intelligence can support such capabilities, however, the realization of these capabilities and especially their integrations still represent an open research issue. So, can a cognitive control approach help? We strongly believe yes, it can. Our research objectives concern the realization of a cognitive control approach supporting abstract thinking features necessary to synthesize flexible assistive behaviors. We pursue the integration of AI knowledge representation and reasoning with automated planning to allow robots to autonomously reason on assistive scenarios and contextualize their behaviors. Koala is a framework we have recently developed to support continuous and proactive assistance in daily home living context. In this work, we extend the representation and reasoning capabilities of Koala in order to support a wider range of scenarios. A source of inspiration from this work has been a research project we are working on called Robotics. One of the assistive scenarios considered in this project concerns cognitive stimulation, where an assistive robot supports the definition and execution of a cognitive stimulation program through the administration of a personalized set of cognitive exercises. Such a robot should internally represent information characterizing the health state of the person receiving assistance, especially the cognitive state in the considered scenario. The robot should also elaborate this information to autonomously infer cognitive impairments and match them with its assistive capabilities. And then the robot should synthesize a personalized sequence of actions administering suitable cognitive exercises. Next slides describe the ontology-based representation and reasoning capabilities developed to fulfill these requirements. As a first step, we have defined a general model suitable to represent and reason about health. We have taken into account the International Classification of Functioning, Disability and Health proposed by the World Health Organization, which represents a well-structured theoretical framework characterizing health from different perspectives. The key assumption indeed of the ICF classification is that the level of functioning of a person is the result of a number of factors that can either be related to the body or to the environment. In this work, we have particularly focused on the parts of ICF called body functions and structures and activity and participation. These two parts are well suited to represent information about functioning of body parts, but also more general information about the social behavior of a person. Thus, considering these parts of ICF, the ontological model has been defined on top of DOLCE, which represents a solid and clearly structured formal background. In general, the concept of the ICF represent qualities of a person with respect to different physical, cognitive or environmental aspects. For this reason, it was natural to model such concept into the developed ontological model as extension to the concept of quality defined by DOLCE. So starting from the concept of quality, we have defined a taxonomy of functioning qualities representing health information of a person from different point of views. On the one hand, we represent qualities strictly correlated to body parts and related physical or cognitive functions, like example attention function, memory function, hearing or seeing. On the other, we represent more general qualities like example communication or mobility that are mainly related to the behaviors of a person and his or her ability to interact with the environment and other people. So according to DOLCE, each quality can be measured and expressed with respect to some dimensional space, modeled as region, In the same way, the level of functioning of the introduced qualities can be measured, and thus a specific type of region has been defined to represent the outcome of such measurements. More specifically, the ICF proposes a set of scores representing the level of functioning of a particular quality. Namely, a score represents to which extent a person is able to use a specific quality. So the minimum score is 0, denoting a full functioning of a quality and thus no impairment, while the maximum score is 4, denoting a full impairment of a quality and thus the inability to use that quality. Screening procedures, like example the mini-mental state examination, could be used to estimate the cognitive functioning of a person and therefore can be taken into account to build user profiles assigning score to the model qualities. So, assuming that such profiles are given as input to the robot, knowledge reasoning mechanisms process these profiles in order to infer the set of cognitive impairments affecting the health state of a person. As can be seen here, we generally have a cognitive profile which is associated to a specific patient that is composed by a number of measurements whose outcomes specify the level of functioning of model cognitive qualities according to the ICF scores. Then, knowledge inference rules analyze these outcomes and identify the cognitive impairments associated to a particular profile. The rule in particular infers a cognitive impairment for each stored measurement, assigning a low functioning level to a quality of a profile. In addition to this knowledge, the ontological model should characterize the assistive capabilities of a robot. To this aim, we have taken inspiration from the taxonomy of functions defined in manufacturing. This taxonomy classifies manufacturing functions according to the effects they have on the quality of some objects or parts of the environment. As can be noticed, this interpretation is quite general and valid for different domains, not just manufacturing. Also, it pursues a clear separation between the capability of an acting entity and its concrete implementation, and the way it performs some function. So, we have integrated the concept of function into the defined ontological model, and we have characterized the different types of stimulation functions by taking into account the effects that these functions have on the model functioning qualities of a person. And as you'll see in the next slides, these functions are used to generally characterize the stimulation capabilities of the cognitive exercise a robot can administrate to a patient. So, as you can see here, we have defined the concept of stimulation function as a particular type of function whose effects concern only functioning qualities of a person. Stimulation functions are associated to cognitive exercise and are thus used to represent their capability and consequently the stimulation capabilities of a robot in charge of administrating them. To support a complete representation of stimulation capabilities, we have considered the defined functioning qualities of a person and defined an analogous taxonomy of functions, which is partially shown here. Although we are focusing on stimulation function, it is important to point out that the general characterization of functions allow us to represent and reason about robots' capabilities in different domains. Then, given a set of known cognitive exercise, an assistive robot should dynamically reason on the associated stimulation capabilities in order to contextualize assistance to the specific impairments of a person. To link knowledge about stimulation capabilities to knowledge about cognitive impairments in a flexible way, we have borrowed the concept of affordance. Broadly speaking, this concept has been used to define opportunities of actions enabled by objects of the environment. Typically used in robotics to enhance the flexibility and adaptability of robot behaviors by reasoning about the actions that can be performed according to the types of objects in a scene. So, to support flexible reasoning and personalization, we have introduced this concept into the defined ontological model in order to allow a robot to autonomously recognize stimulation opportunities. Namely, given a set of inferred impairments of a person, affordances are used to dynamically infer opportunities of stimulation enabled by the capabilities of the cognitive exercise known by the robot. In this way, a robot can autonomously infer the subset of exercise that can afford or in other words, have positive effects on the specific cognitive impairments of a person. Here, with more detail, we can see how the concept of affordance is defined into the ontological model. In particular, it can be noticed that an affordance is characterized as a relational concept linking cognitive exercise to cognitive impairments. Inference rules allow a robot to autonomously identify correlation between impairments and exercise and accordingly infer stimulation opportunities. At the end of the inference process, therefore, a robot knows which exercise can afford the cognitive impairment of a particular person. However, the number of exercises that can afford the impairments of a person could be huge. The last reasoning step is necessary to analyze the extracted exercise in order to identify those that may have a higher impact on the health state of a person. We have thus developed an ontology-based recommendation system to rank the obtained exercise and identify the most relevant ones with respect to the stimulation objectives. These exercises are those that should be considered by the robot to synthesize effective and clearly personalized stimulation plans. The recommendation system combines a user profile vector encapsulating the ICF scores of the measured functioning qualities with an incidence matrix denoting for each exercise the functioning qualities it can afford. The obtaining ranking vector estimates the significance of each exercise with respect to the health state of a person. As can be seen from the matrix multiplication, ranks are computed such that higher values are assigned to exercises that stimulate the most seriously impaired qualities and to those that address the widest range of impairments. So, this concludes the contribution of our work presenting a novel domain ontology for representing and reasoning about health and assistance. Now, to evaluate the efficacy of the developed representation and reasoning functionalities, we have made an experimental evaluation on a randomly generated dataset. Specifically, we have generated 10 user profiles by randomly assigning ICF scores to functioning qualities. Then we have defined 18 sets of cognitive exercise determining the assistive capabilities of the robot. We have considered a growing size of these sets, starting with a minimum of 10 known exercises and ending with a maximum of 500 exercises. Each cognitive exercise in particular has been modeled by associating a random number of stimulation functions for a maximum of 5 functions per exercise. And the table here shows the obtained results. As can be seen, the higher the number of exercises, the more the number of stimulation opportunities inferred for a given set of users. The higher the number of stimulation opportunities, the more the number of recommended exercises. And then, the higher the number of combinations to consider for recommendations, the higher the knowledge to process. And the performance trend is however quite efficient, as can be seen, confirming the technical feasibility of the proposed approach. Indeed, the reasoning process takes about 700 milliseconds in the worst case, with 500 stimulation exercise processed for each user profile. Then, to assess also the quality of the generated recommendations and thus the personalization capability of the approach, we here shows another experiment we have recently presented at Roman, where we have integrated this approach with a dialogue-based system for the actual administration of stimulation plans. In this case, we have focused on just 3 users and modeled a set of existing cognitive exercises that are usually used in this context. The radar chart here shows the outcome of the reasoning process. And we can see how the approach is capable of effectively assessing the significance of known exercise with respect to the cognitive impairments of the considered users. For example, no significant recommendation is generated for user 1 who has no particular compromised cognitive functions. Instead, in the case of user 3, the system computes a high recommendation value for exercise F, which addresses some significantly impaired cognitive function of the user, like, for example, working memory or retrieval and processing. In conclusion, the contribution of this work has concerned the definition of a novel domain ontology characterizing health needs of users and assistive capabilities of robots. Also, we have developed knowledge reasoning mechanisms based on the concept of affordances to support the synthesis of personalized cognitive stimulation plans, and experiments have shown the technical feasibility of the proposed approach. So, future works will particularly focus on the deployment of this approach on robotic platform and evaluation with real users and clinicians. In this regard, we plan to further investigate explainability in order to help patients in understanding why a particular exercise is important for his or her health, but also help clinicians in understanding the type of intervention needed. That's all for my presentation, and I thank you for your attention.